Hey everybody, we are starting the next section about additional aspects of chemical equilibrium, and we're going to talk about the common ion effect and its effect on equilibrium. So let's imagine that we have a solution of acetic acid. Okay, that's what we have here. I don't know what the heck all this stuff is going on here. Okay. But we have this guy. Okay. Now, if we have that solution of acetic acid, we know because it's a weak acid that exhibits equilibrium. Okay. I'm going to move my microphone if you hear something crazy. You know that it's me. Okay. So, now, that weak acid equilibrium is dependent not on how much water is there, but is dependent on how much hydronium ion is there and how much acetate ion is there. Okay, so if we add acetate ion to this solution, Le Chatelier's principle says that we're going to shift this direction in order to compensate. Okay, we're going to shift this way. So that means if there is some source of acetate in here, to begin with, let's say instead of all coming from here, let's say we had like some sodium acetate. Okay, sodium acetate is completely soluble, so that means that you'll only find it as acetate. That means that we'll have some acetate ion in the reaction to begin with. Okay, sodium is a spectator, so we don't have to worry about that. Okay, now that acetate ion floating around in solution is going to make the reaction shift to the left. So by shifting to the left, that decreases the H3O concentration. If the hydronium ion concentration decreases, that means the pH will go up. So the common ion effect is what happens when we have some of the ion, of either ion, this one or this one, in the solution before we begin, and that's going to affect the pH. Okay, so let's take a look at this problem. Okay, so take a minute, pause, write down whatever you want to do. Okay, and I'm going to take this and I am going to, oops, there's the Ka, the expression for that. Okay, let's go here. Okay, so all I did was copy and paste this in here. I'm finally getting smart. So once you have copied and pasted this here, now we can do some math, okay, or some chemistry. Okay. Now, pH of the solution, okay, so we want to calculate the fluoride ion concentration. Well, the fluoride ion concentration is dependent on the weak acid equilibrium of HF plus H2O is in equilibrium with H3O plus F minus. Okay? The biggest issue that I see students having, I'm addressing it right now, and I will address it as often as I can, is that students make up reactions for an acid equilibrium. Okay, the fluoride ion is only found here. There's no fluoride in HCl. So the only way that we can get to the fluoride ion concentration is by doing the equilibrium reaction of HF. That's it. Okay, so don't get confused. And the HF here, the HF is completely forgot what I was going to say. But okay, so the HF here is a weak acid, and we're going to do this. So here's what we get. Let's set this up. Now here's the key. This is what makes the common ion effect slightly different than a traditional problem. Well, what's the initial concentration of HF? Well, 0.2 molar. Okay, we don't care about water. We don't have any fluoride floating around, but we do have an initial concentration of H3O+. Where do we get the initial concentration of H3O+? It's from the HCl. So this initial concentration is not 0, it is 0.1. Okay, so now we do our chemistry. Okay, well, we know that this is going to still shift this way because there's a 0 over here, so this is still going to be minus x plus x plus x, and so this is going to be 0.2 minus x. This is going to be, I don't know why that happened, but I'm going to, okay, this is going to be 0.1 plus x. This is going to be x. Okay, so we'll do our, that's ICE. Boom. Okay. Now the equilibrium expression for this is, let's see, Ka equals the concentration of H3O plus times the concentration of F minus all over the concentration of HF. Now, this is equilibrium concentrations, so we actually have to spend a little bit of time plugging this in using the x's. So, I moved this up too soon because, okay, so 6.8 times 10 to the minus 4. So the Ka is 6.8 times 10 to the minus 4. That equals the concentration of H3O plus 0.1 plus x times x, the equilibrium concentrations, this bottom row, over 0.2 minus x. Again, let me clean this up because I want to make sure that it's nice and neat and clean so that you can, okay, see it? And that goes in parentheses. Okay. Okay. Now, if you really wanted to, you can do the quadratic equation, plug it in, solve it. But we're going to assume that x is really small. Now, by assuming that x is really small, actually, what I can do, by assuming that x is really small, that means we can get rid of this x, and we can get rid of that x. Okay, that helps us out a lot, because 0.1 plus some very, very, very small number is still going to make us somewhere around 0.1. Okay, so now at this point, we've done all the math, and we can figure out, we can solve for x. So 0.1 over 0.2 is a half. Okay, I'm gonna show you that having math skills can help. 0.5x, 6.8 times 10 to the minus 4. So a half, we're going to multiply by 2, and so that's going to be 1.36 times 10 to the minus 3 equals x. Okay, let me just double check to make sure. Okay, so 6.8 times 10 to the minus 4 times 2, right, okay, that equals x. That happens to be the concentration of fluoride ion, because x is the concentration of fluoride ion. But what if, the problem doesn't ask for it, but what if we wanted the pH? pH. Okay, well, the pH is equal to the negative log of the hydronium ion concentration. pH equals the negative log of the hydronium ion concentration. Well, what's the hydronium ion concentration? Well, the equilibrium hydronium ion concentration from our ICE chart is 0.1 plus x. So we can go down here and we can go over here, 0.1 plus X equals the concentration of the hydronium ion. So 0.1 plus 1.36 times 10 to the minus 3. Okay, so 0.1 plus 1.36 times 10 to the minus 3. Okay, equals, so the hydronium ion concentration equals, in this case, 0.10136. Okay, so that means the pH equals the negative log of 0.10136. So what's the negative log of 0.10136? And that equals, the pH equals 0.99 pH units. Just for fun, what I want to see if I can illustrate this. Okay, what is the pH of just the 0.1 molar, let's say, of the 0.1 molar HCl? What is the pH of 0.1 molar HCl? Well, it's the negative log, because it's a strong acid, negative log of 0.1. Well, the negative log of 0.1 is equal to is equal to 1, so the pH is 1. So we've done a lot. Okay, we calculated the fluoride ion concentration in this mixture, but we've also seen something interesting. Okay, this is your bonus lesson here, is that when we mix acids, the stronger acid controls the pH. Okay? By adding all of that HF, which is a weak acid, we only change the pH of the solution by 0.01 units. So what is the pH of just the HCl? 1. What is the pH of the HCl plus HF? Still just about 1. Okay, so whenever you mix acids, yeah, you have to go through this ICE chart process, and you kind of have to figure all this out. But just know that if you're asked for the pH, you just need to pick the stronger acid, okay, and then work your way through that. Okay, so I hope that at the by the end of this video, you have understood what the common ion effect is. We'll go back up here. How the pH, or about how adding ions will change the amount of material at equilibrium, okay, or the amount of products at equilibrium. And the bonus is that I hope that you see that when you mix acids, the stronger acid will be controlling the pH.